Hi everybody, this is Jim Corkins, and we are going to start the next section, and this is centripetal acceleration. Now, we've talked about centripetal acceleration a while ago in motion, but we're going to revisit it because later on we're going to talk about centripetal forces. Okay? If you haven't done any of the reading on centripetal acceleration, it's in these OpenStax chapters listed here for Physics 101 and 111. And Survey Chapter 8. In Physics 121, it's in these chapters here, and in night, it would be Chapter 12. And for all of our physics courses, it would be in Coletta Chapters 9 and 10. Well, basically, you have experienced centripetal acceleration and centripetal forces, and you experience it all the time. Anytime you turn your car, anytime you're moving in a circle, anytime you're on a roller coaster. So we're going to talk about what centripetal acceleration is and how it affects your motion here. So the first thing that we're going to do is we're going to actually start off with a kind of a quiz question. And this is a review of splitting up vectors, acceleration vectors, into its components, and seeing how acceleration affects velocity. And we did this in the chapters right around two-dimensional motion. But we're going to do it again and just see if you could remember it. Okay? And this is going to help lead into centripetal acceleration. So here we go. So you have an acceleration vector pointing down and to the right, affecting this particle, and this particle is already moving just to the right. So how will this acceleration affect the motion of this particle? Will it slow down and curve it downward? Will it slow it down and curve it upwards? Will it speed it up and curve it downwards? Will it speed it up and curve it upwards? So take a moment and think about it, and pause the video and answer the question. Okay, so pause now. All right, so hopefully you pause the video, and now we're getting a chance to try this out. So what I'm going to do is I'm going to mark up this document by hitting the comments folder right here. I'm going to put that sub window back in, and now I'll have access to the pencil. So what I'm going to do is I'm going to split up this acceleration vector into its left and right components. Okay? So this acceleration vector looks like it's pointing down and to the right. So I'm going to split it up into those components. Okay? And in fact, I'm going to extend this out so it'll make this vector really easy to draw. So that's the vector head. So I've got to split this diagonal into its x and y components. Well, describing this vector, it says that this vector, it looks like it's pointing down, but it's also pointing to the right. So this acceleration vector is going to have a negative y direction acceleration, and it's going to have a positive x direction acceleration. And we already have a velocity vector that is pointing in the x direction, okay? So when you have a velocity vector pointing in the x direction, the positive x direction, and you have an acceleration pointing in that same direction, that is the definition of speeding up. So that x direction vector here, the a sub x direction vector, added to that velocity vector would actually cause its overall velocity to increase within the next time unit. So we know this object is speeding up. Okay, so it's going to be either C or D. Now the question is, what else is it going to do? Is it going to curve it upwards or curve it downwards? Well, this acceleration vector is actually pushing down on this particle. Okay, so y direction wise, I'm going to redraw it over here. This y direction, this particle has no initial velocity in the y direction, okay? But it has an acceleration in the y direction, the negative y direction, okay? And so add this acceleration vector to this initial velocity of 0, and what you will find is that if this is the 0 second mark, at the 1 second mark, it will now be moving down. It'll have a downward final velocity vector after that 1 second. That will be the same size as this initial acceleration vector. So essentially, if you consider this acceleration vector a force, it is going to be pushing down on this velocity, this particle. Now that's not going to cause this y direction acceleration vector is going to cause it to curve downwards. So the answer is C to this. But this, I want to point out that this acceleration vector, and here's kind of the point of the review, this acceleration vector in the y direction, the negative y direction I should say, is neither going to speed up nor slow down this x direction acceleration vector, x direction velocity vector. So all this, as long as this vector right here is at a 90-degree angle to the velocity vector, this acceleration is going to neither speed it up nor slow it down. Only the x direction acceleration vector is going to speed up or slow down this object. So this one is just going to turn it. It's going to turn it downwards. So it's going to cause this guy to begin to move down. While this acceleration vector right here is going to cause it to speed up in the x direction. So what's probably going to start to happen is this thing is going to start moving like this. So it's got that initial velocity vector that it started with, and then now that acceleration at this point, it's now moving down and to the right, which means that acceleration vector has added a second velocity vector to it. Okay. And this next velocity vector is going to be equal to the addition of this acceleration vector plus this velocity vector. So this is going to be Vx plus Ax. So that vector is going to be the addition of those two vectors. And not only that, this vector downwards is going to be the acceleration in the y direction vector, which is going to then in turn become the velocity vector in the y direction, which will be negative. Okay, so that's what's kind of happening. And again, the whole point is seeing how an acceleration vector can turn an object, but not necessarily speed it up and slow it down. And when that acceleration vector is at a 90-degree angle to the velocity vector, that will cause it to turn, but not necessarily speed it up or slow it down. Okay. I'd like you to try this one out on your own. Okay. So pause the video, and I want you to do what we just did before. Split up the acceleration vector into its components of x and y direction, and see how that will work in speeding this up or slowing it down. So please pause the video now. Okay, well, again, this one has a negative x direction velocity vector, and now we have an acceleration vector again that is pointing down and to the right. That means it's going to be pointing to the right in the positive acceleration and positive x direction, but again, it's still going to have a negative acceleration vector in the y direction as the last one. Okay, so this velocity vector added to this acceleration vector, they're going to be in opposite directions. So the positive acceleration vector in the x direction added to this negative velocity vector in the x direction is going to just this vector and this vector, when you add that together, it's just going to be slowing it down. So the answer is going to be A or B. But again, this negative acceleration vector, which is at a 90-degree angle to the negative acceleration vector in the y direction, is at a 90-degree angle to the negative velocity vector in the x direction. So that is going to start, that acceleration vector here is going to start pushing down on this particle. And it's going to start curving it downwards. So the answer to this is slowing down and curving downwards. Okay? All right, well, how do you feel about that? Was that a good review? Well, here's the last one for you. And I want you to pause the video and try this out. And this time, I'm just going to give you the answer to it. But pause the video, try it out on your own. Split that acceleration vector into its vertical and horizontal components and see how those add to the velocity vector or turn the velocity vector. So please pause the video now. Well, in this case, this acceleration vector is going to be curving it upwards, but it's going to be slowing it down because the x direction component is opposite the direction. So it's pointing in the negative x direction while the velocity vector is pointing in the positive x direction. And the vertical component is pointing in the positive y direction. So this is going to slow it down and curve it upwards. All right, let's try to apply what we've learned to circles and rotation, okay? So I'm going to switch over to a PowerPoint presentation. So let's say we have, right here at this point, we have something turning. It's going to be turning in a circle, okay? And let's say all of these velocities are the same. So let's say that the magnitude of V1 is equal to the magnitude of V2 is equal to magnitude of V3 is equal to magnitude of V4. So let's say all of these are 3 meters per second. So this object is going to have the same speed the entire time, right? This is like if you're driving your car in a circle. So we're looking down on it and you're driving your car in a circle. And at this point, the center of the wheel is going to be right here. So at this point, your car is moving upwards. Here, your car is moving to the left. Here, your car is moving down. And here's your car moving to the right. And so your speedometer would say just 3 meters per second the entire time. Okay? Okay, well, let's find out what's going on here. Well, let's take just these two velocity vectors, V1 and V2, and compare them to each other. Okay? And what we're going to do is we're going to add those two velocity vectors together. Well, technically, even though the speed is the same, your velocity has changed direction. It's gone from pointing upwards to pointing to the left. And since acceleration is the change in your velocity, what's going to be happening, and I think we've already done this in two-dimensional motion, is this is going to, when you add these two velocity vectors together, V1 and V2, right, that is kind of meaningless. But if you reverse the initial velocity vector V1, okay, and then add that to V2, then what we have is that equation right here, where the final velocity is equal to the initial velocity plus acceleration times time. Well, you subtract the initial velocity vector onto the other side. And so the addition of the V2 plus the negative V1 vector is the acceleration. So this hypotenuse vector, which is the addition of V2 minus V1, that is the acceleration vector. Well, if you add that up unit by unit, and I've done a pretty good job at making sure those are very consistent in distances, that this acceleration vector is pointing towards the center, okay? But it's a diagonal here. So let's break up that acceleration vector in its x and y components, just like we were doing in the last couple exercises, okay? Well, now if we take those component vectors and we can then hinge the x direction acceleration vector to the v1, and we could hinge the negative y direction acceleration vector to v2. Well, what you find out is those acceleration vectors are at a 90-degree angle to those velocity vectors, which means they're not going to speed it up nor slow it down. And those acceleration vectors are pointed towards the center of the circle. So they're just responsible for turning it. In this case, those acceleration vectors are going to be turning the car from moving up to moving to the left. They're going to be turning it counterclockwise. And if we continue with this acceleration and continue with those acceleration vectors, what you would find out is that you would have the same magnitude acceleration. So each one of these vectors is the same size, and at each one of these points, they're pointed towards the center of the circle. Well, that is a type of acceleration called centripetal acceleration with a P, not F. Centrifugal acceleration is a non-term. It's not a real acceleration. Okay, so centripetal acceleration is Latin for center seeking. In other words, the at point where your velocity is moving upwards, in order to go from v1 to v2, you have to accelerate towards the center of the circle. And in order to get from v2 to v3, you have to have an inward pointed acceleration the entire time. And to go from v3 to v4, you have to have that acceleration vector pointed at the center, and so forth. And as long as this is a perfect circle, then that means the acceleration towards the center of the circle is a constant magnitude, meaning that it's the same size at each point in time. Okay. So that is just a real quick explanation for how that radial, it's also called radial acceleration. Centripetal is also called a radial acceleration. How that can change a velocity vector's direction, but not speed it up nor slow it down. So even though this object has a constant speed, not constant velocity, it doesn't have a constant velocity. The velocity vectors are pointed in different directions at each point in time. But it's got a constant speed, meaning the magnitude of these or the size of these velocity vectors is the same. So if it's long, what this is saying is this has got a constant speed, but it's accelerating towards the center the entire time. And that's how important this velocity vector is it actually will pull something towards the center of the circle. Well, now that we have a basic understanding of what centripetal acceleration is, let's investigate it a little bit more. And we're going to investigate it in terms of what we've been talking about with rotational motion, specifically rotational or angular velocity and rotational or angular acceleration. Okay? So it's interesting that what centripetal acceleration is actually the velocity vectors squared divided by the radius. Okay? So how you actually calculate that acceleration vector is you take the square of the velocity vectors and then of the velocity, and then divide it by the radius, okay? And that will tell you the centripetal acceleration, okay? Another way of saying that is you take the radial, and this should be noted that this is the radial omega. So this is the angular velocity, the radial angular velocity, square it and multiply it by r, and you have the centripetal acceleration, which I'm going to subscript with a c. Okay, and that tells us that these vectors are always pointed towards the center of the circle. Okay. Interesting thing about this is if you have a ball, you've thrown a ball in this tube, and let's say this ball is moving in this tube, around in this tube, around in this tube, And when it gets to right here, the question is, which direction is it going to move? Is it going to keep curving? Is it going to move in this direction and land back in there? Or is it going to slide off and then miss? Is it going to go straight? Or actually will it bend out? So based on what you learned from the last slide, what direction do you think this ball will move when it gets to this point right here, when it's going around the inside of this tube? So go ahead and pause the video and think about it. Okay, well, at any point in time, this ball, and I should put the ball on the inside of the tube, this ball is going to be moving at a tangent to the circle. And that's its tangential or linear velocity, right? It's pointing in the negative x direction here. Here it'll be pointing in the negative y direction. Here it'll be pointed in the positive x direction. Here, well, the tangent to the circle should be straight upwards. So since this object is trying to go in a straight line the entire time, it's this track which is pushing it towards the center of the circle at every one of these points. Okay? And so it wants to go in a circle. Okay? So for example, you're driving your car, you want to go in a circle, but as long as your car is driving counterclockwise, it's your car tires or your seat belt. If you're doing donuts in your car and driving in a counterclockwise circle at a constant speed, which side of your waist do you feel your seat belt biting into? Well, you'd feel the right hand side of your waist it kind of feels like it's pulling on you. Well, that's the centripetal acceleration, pulling you to the center of the circle. You want to go in a straight line. You feel like you want to go outwards, but really you want to go in a straight line, but your seatbelt keeps pulling you towards the center of the circle. So the answer to this is C. Okay? It's because you always want to go to the tangents, okay, at every point in time. And this is your linear velocity vector. It's also called your tangential velocity vector or translational velocity vector that we covered in 5.0. Okay? Well, what we also learned in 5.0.1 is that you can speed up and slow down as you're moving in a circle, right? So we've seen this one before, this motion diagram before. This is 1 second, this is 2 seconds, this is 3 seconds, this is 4 seconds, 5 seconds, and 6 seconds. So it looks like it covers just a little bit over of a half revolution. And it looks like it's doing about a half revolution in 6 seconds, which is going to be 1/12 a revolution per second. Okay? So that looks like what's kind of happening here, right? At this point, its velocity vector, which it's just made it just past it. So if this started out with an omega of 0, this is actually going to be at omega will probably be at 1/12 a revolution per second. Okay? Okay, so it had gotten all the way to here. Well, it's speeding up that entire time, right? The dots are closer together and they're getting further and further apart. What this is telling us that now that we will have a velocity vector, and these green vectors are velocity vectors. They're the tangential velocity vectors or linear velocity vectors. And the omega is going to be the 1/12th revolution, so this is its turning velocity, rotational velocity. Anyways, so not only now will it have that centripetal acceleration vector, but now it's going to also have a tangential velocity vector as well. So I'm going to call that A sub t, tangential velocity, and this is going to be A sub c. So at this point, it's moving up and to the left. It's got an acceleration vector up and to the left in line with its velocity vector. And it's got a center-seeking acceleration vector. Over here, it's moving down and to the left, and it's got an acceleration vector that is increased because it's speeding up. Well, actually, it's got a constant acceleration vector, so its velocity vector is increased, but it looks like its tangential acceleration is the same. But since its velocity vector is increasing, and since centripetal acceleration is equal to the velocity vector squared over the radius, you will see that the acceleration vector will actually can grow and increase along with this velocity vector, and that's because the tangential acceleration is increasing the velocity, and which then in turn will increase the centripetal acceleration. So this, even though it has a constant tangential acceleration vector right here and right here and right here and right here, they're all the same sizes, okay? That is increasing the velocity vector, which in turn, right here, will then increase the acceleration vector, okay? So now, not only do we have to think of tangential velocity, tangential acceleration, omega, and alpha, but now we have to think about a centripetal acceleration as well. Okay? So just to remind people of some of those acceleration vector equations, the tangential acceleration is just going to be r times alpha, which is the alpha rad, you know, the 2 pi alpha. And the radial acceleration, which is A sub c, which is also the radial acceleration, is that tangential velocity vector squared divided by r, or it's also omega squared times r, okay? And both of these radial accelerations, we're just going to use probably the instantaneous version of it, okay, in Physics 121. Okay, so this is just to remind people about those different, how those velocity vectors and acceleration vectors and alpha and omega are interlinked here. Okay, so alpha would be in this direction, it's going to be positive, omega is going to be positive, and this velocity vector would be changing at any point in time. So, and then we have that tangential, velocity vector. We also have a tangential acceleration vector, and we're going to have a centripetal acceleration vector. Add those two vectors together and you get that overall vector, but I'm more worried about the components for now. So let's do some practice problems, okay? Suppose you had a coin that is glued to this turntable. So this coin on this turntable is going to be rotating in the same direction that the turntable is spinning. So this is like looking down on the top of a record player, okay? And so this coin is rotating counterclockwise along with the turntable, and it's been rotating this direction and then speeding up as it's doing so. And as it's been rotating, we're catching the instance it's reached right here, okay? So we're going to have to answer a bunch of questions regarding this in terms of linear and angular for a coin that is on a turntable and the turntable is speeding up as a coin is glued to it at this instance. So what I want you to do is I want you to answer the question for the tangential or linear velocity of the coin at this point, the linear acceleration of the coin at this point, the centripetal acceleration for the coin at this point, and the angular velocity and angular acceleration of the coin / turntable during this entire time. Okay? So go ahead and pause the video and try answering each one of these questions. Okay? So as this coin is spinning around this turntable, it's going counterclockwise. So the turntable is turning in the positive z direction. Okay, and you've got to answer your questions in terms of x, positive positive y, positive z, negative x, negative y, negative z. So this turntable is rotating counterclockwise, which we've established as positive z direction. And since it's speeding up, so the omega is going to be positive z. And since it's speeding up, that means the angular acceleration vector is going to be in the same direction as the angular velocity vector. So that's also going to be in the positive z direction. Okay. So let's talk about the tangential acceleration velocity vectors and centripetal or radial acceleration vectors. So this wheel is turning. When it gets to this instance, it looks like the coin would be moving in the negative x direction. So at this instance, it looks like the coin is going to be moving with a velocity vector in the negative x direction. And since it's speeding up, that means the linear or tangential acceleration vector would be also pointed in the same direction, in the x direction. Because that's the definition of speeding up. The velocity vector and acceleration vectors are in the same direction. However, it's got an additional acceleration vector on it that will just be turning it, right? The glue is kind of a friction force which is pushing it towards the center of the circle. So its centripetal acceleration vector is going to be directed downwards in the negative y direction. Okay? So objects that are turning in circles can be a little complex because they will probably have a tangential velocity vector, a tangential acceleration vector, a centripetal acceleration vector, an angular velocity vector, and an angular acceleration vector. So they have five different or similar, depending on how you look at it, types of vectors acting on them simultaneously. Pretty neat. Okay. Let's try another case. Okay. So this is, I've changed a bunch of the conditions. So now we have a turntable or a record player with the same coin glued to it, and x's and y directions are in the same as they were in this last problem. Z out and Z in are in the same problem as this other one. So our cardinal directions haven't changed. However, this wheel or this turntable is rotating, and it looks like it's rotating clockwise. Not only that, it's slowing down as it's turning clockwise. So what I want you to do is I want you to answer all these questions that we just did before for this case where this coin is at this instance right here during a clockwise rotation. So pause the video and try it out. Okay, well, let's take care of the angular stuff first. Well, the wheel is rotating clockwise. which is going to be the negative. It's going to have a negative omega, which is going to be in the negative z direction. But we said that it's slowing down as it's doing so. So that means its angular acceleration vector has to be opposite the angular velocity vector for it to slow down. So this is so angular acceleration is going to be positive z. All right, we've got that done. Okay, well, now we know this thing's rotating clockwise, and this coin has reached this instance right here. And it looks like the coin is going to be traveling in the negative x direction. Just happens to be so at this point. And not only that, it's going to, since it's slowing down, that means it's going to have a positive acceleration vector in the x direction for its tangential or linear acceleration. Because that means it's slowing down, right? A leftward velocity vector, for it to slow down, has to have a rightward pointed acceleration vector. Okay? Well, the centripetal acceleration vector is going to be pulling this coin towards the center of the circle. So that's going to be pointed in the positive y direction. Okay? So this is this problem, and hopefully you're getting a good point. Let's try one more. And this one is going to be an easier, let's do right here. Let's do speeding up as it's rotating clockwise. Okay, so this wheel's rotating clockwise, and the wheel is speeding up. The coin is at this point here on the left side of the turntable. So go ahead and pause the video and try this one out. Okay. Well, its angular velocity vector is going to be negative. Okay, so that's going to be in the negative z direction. And if it's speeding up, that means its acceleration vector is also going to be in line with the angular velocity vector. So that is going to be negative z as well. Okay, well, let's move on to the linear stuff. The wheel, the coin is at this point right now as the wheel is turning in the circle. So at this instance, you can see my cursor is moving upwards. So this coin would be moving upwards in the positive y direction, and it's speeding up as it's moving in the positive y direction. That means it's got a positive y direction velocity vector and positive y direction acceleration vector. Okay. At this instance, the coin is also being pulled towards the center of the circle, which is in the positive x direction, by the centripetal acceleration vector. Cool, very cool. Okay, let's try this one last one real quick. What if it's at constant speed as it's rotating? This way it's going to be counterclockwise. So go ahead and pause the video and quickly answer those 5 questions. And this is a coin rotating this turntable is rotating counterclockwise at a constant speed. All right, try it out. All right, well, here it's going to have a positive directed omega, but since it's rotating counterclockwise and it's not speeding up or slowing down, it's got a constant speed. Well, its acceleration vector is going to be 0, but its velocity vector is going to be in the positive z direction. Well, if my cursor, which is moving counterclockwise, gets to the right-hand side, that velocity vector is going to be moving up in the positive y direction. But since it's moving at a constant velocity, its acceleration is going to be 0. So its tangential acceleration is 0, but its velocity vector is in the positive y direction. At this instance, the coin is being pulled towards the center of the circle by the centripetal acceleration, v squared over r, and that's going to be in the negative x direction. Okay, I hope you learned a lot from that. Let's do one last exercise, okay? And this is in example tutorial page 4.24. And what you're going to do is you have a wheel, and I've changed it a little bit. For our case, we have a wheel, and this wheel is going to roll down this track, roll across A, roll across B. When it gets to C, it's going to start rolling down here, and it gets to D, it gets to E and F, and at F, it's going to get launched into the air. So this is the end of the track at F. Okay. And then it's going to get launched in the air where it passes through G and then probably hits the ground somewhere later on. So what I want you to do is draw the vectors for the tangential velocity vector, the tangential acceleration vector, the centripetal acceleration vector, if it's there, omega and alpha. Okay. All right. Go ahead and pause the video and try this out. Okay, well here we go. We've got this wheel, and it's going to be rotating, and it looks like it's going to, for it to be moving down this track, and it's not a frictionless track. There is going to be static friction, so the wheel can rotate. And then when it gets launched in the air, then the wheel's going to be rotating without friction, but it'll have sped up to some point there. Anyways, for this object to be rolling down this track and moving to the right, it looks like it's going to have to rotate clockwise the entire time. So at A, it's going to have a negative omega. So at A, it's going to be rotating clockwise. So that's going to be a negative omega. Okay. And when it's at A right here, will it be speeding up or slowing down or constant velocity at A? Well, since it's going on the downward portion of the track, it's going to then be speeding up too. So its negative angular velocity vector is going to be complemented by the negative angular acceleration vector. All right. Now let's note the linear components. Well, it's going to be moving down the track here. So its velocity vector is going to be down the track. And its acceleration vector is going to be in the same direction for it to speed up. So its linear velocity vector and its angular acceleration and its linear velocity vector and its linear acceleration vectors are going to be in the same direction. So that's V sub L and A sub L. Since it's not on a curved track, the centripetal acceleration vector will be 0. Okay? All right, let's try B. Why don't you try B on your own and see how you do? Okay. Well, in the absence of air friction or kinetic friction, this object is still going to be rolling clockwise. But let's look at the velocity vectors real quick. Let's look at the vectors of this before we answer questions about the angular acceleration. Well, at this point, its velocity vector is going to be to the right, but its linear acceleration vectors or tangential acceleration vectors is going to be 0. It's going to be kind of coasting. It's not going to be speeding up nor slowing down. Okay. And since it's not turning in a circle, its centripetal acceleration vector is going to be 0 as well. Well, the linear acceleration vector is the angular acceleration vector times r. So that means the angular acceleration vector is also going to be 0 because the wheel is rotating at a constant velocity through this horizontal straight path. Okay, now it's going to start getting interesting. At C, I want you to try answering C, D, E, and F. Let's see how you do. So pause the video and try those out for your own. Okay, well at C, this guy is going down and to the left, just kind of like up here. So it's got a down left velocity vector. And it's on a downward portion of the path, so it's going to have a down left acceleration vector. Well, that means omega is going to be, it's going to rotate, it's going to keep rotating clockwise, and since it's speeding up, it's going to start speeding up in that direction as well. Let me move these guys slightly. I'm actually going to put notes on the top of this. And negative alpha at this point. But here's the interesting thing. It's in a kind of a bended portion of this, right? Well, if you imagine that this bended portion is a big circle, it's going to have an acceleration vector that is pointed down and to the left. Okay? Its linear velocity vectors and linear acceleration vectors are going to be at a tangent to this circle right here, which is why it's also called tangential velocity and tangential acceleration. So those are going to be pointed down and to the right, but the centripetal acceleration vector is going to be pointed towards the center of this imaginary circle I've drawn. So it's going to be pointed down and to the left, while it is speeding up in the clockwise direction. All right, let's try D. Well, D is moving to the right, so its velocity vector is going to be to the right. However, it's going in between a portion where it's speeding up and then slowing down. At this interchange, I'm guessing since it's switching over, at that instance, in that interchange between speeding up to slowing down, it's actually going to have an acceleration, a linear acceleration or tangential acceleration of 0. It's that weird moment where it's at that instance, it's a little undefined. So it's basically 0, okay? And it's still going to be rotating clockwise, but since its A sub L is 0, that means the alpha is also going to be 0. But it's still accelerating in a way. It's going to be accelerating towards the center of the circle here. Okay, this is the inner portion of a circle. So it's going to be accelerating towards the center of the circle, even though it has no tangential acceleration or no angular acceleration. All right, let's go to E. Well, for E and F, I'm going to just draw a big circle for both of these. Okay, at E, it's moving up and to the right, and it's accelerating up and to the right at a tangent to this circle. Hopefully that looks good. But it's going to be accelerating down and to the right. And it's going to be rotating clockwise. Ooh, I actually just made a mistake. I'm sorry. It's actually slowing down in a linear direction, right? Since it's moving upwards, it's going to be slowing down as it's going upwards. So its tangential acceleration vector is actually going to be down and to the left as it's moving up and to the right. And that's because it's slowing down. Glad I caught myself there. Well, since it's slowing down and it's got a negative omega, its alpha has to be positive. And that's what helped me kind of catch my mistake. All right, finally at F, it's going to be moving horizontally. Okay, But it's kind of like F is kind of like this instance right here, or like at D, where it's going from slowing down, and then if this track continued, it'd be going to speeding up. So it's going to have no tangential acceleration. However, it is going to have a centripetal acceleration vector straight down, okay? Its omega is still going to be negative, but its alpha will be 0 since its tangential acceleration is 0. All right, now it's launched in the air, and now it's moved to G. At G, it looks like it's moving down and to the right. And it will have a negative omega because it'll still be spinning as it's in the air. It's not going to come to a stop. And this is going to be interesting on how I have to do this. But it will have a down and to the left centripetal acceleration vector. If you imagine G as one big circle, right? Right? And it's going to be speeding up as it's moving down and to the right. So its linear acceleration vector, which is over here, its linear acceleration vector is going to be in line with that linear velocity vector, which means it's going to be speeding up, so it's going to have a negative directed angular acceleration vector. Well, just a minor thing, I'm going to reposition this acceleration vector over here so we could add those two together, okay? I'm doing this just to make a point, because when we were doing these problems in motion, what we had pointed out was in motion, when a ball is in the air, it's actually got only one acceleration, which is gravity. Well, that's kind of not true, sort of. It's going to have a tangential acceleration vector and a centripetal acceleration vector. When you add those two up, that actually comes to be your gravitational acceleration vector, 9.8 times 9.8 meters per second squared. So it's weird. Once a ball gets launched in the air, it will have a constant acceleration vector down, right? And that would be downward by gravity. But really, from a matter of perspective, that gravitational acceleration vector is the total acceleration, or the addition of a tangential acceleration and a centripetal acceleration. And it just happens to add up to be G no matter where it is when it's in this type of motion. It's going to have a G-directed vector there, a G-directed vector here, a G-directed vector straight down, and then kind of like over here at point G, it's directed there. Well, those are the culminations of an acceleration vector, a tangential acceleration vector, and a centripetal acceleration vector. And let me see if I can draw it correctly. Tangential acceleration vector, centripetal acceleration vector. Over here, the tangential acceleration vector is 0, right? Right here, F is kind of like at this point here. So it's got no tangential acceleration vector. But its centripetal acceleration vector will become the gravitational acceleration vector at this point, right here, if you've thrown a ball in the air and it's at this point in its path. Throwing it here, it reaches this point, and now it's this point right here. At the top of the path of this thing being flung in the air, it will just have one acceleration vector pointed down, which is G, but actually that's the centripetal acceleration vector, while the tangential acceleration vector is 0. And it's moving just to the right. So it's interesting, F is actually kind of like the same thing as a ball thrown in the air and it's reached the apex of its path. It's just moving to the right and it's accelerating straight down. Interesting. Well, I hope this helps you understand centripetal acceleration a lot more. Okay? And so that ends our conceptual portion of centripetal acceleration. The next part is going to be the second part, which is how do you apply centripetal acceleration to forces using force diagrams. So there's going to be some force diagrams that we're going to review. Okay? Have a nice day.